These people, dressed as they are, come from all over the United States to make deals here in the marketplace of America. Let's make a deal. And now, here's America's top freighter TV's big dealer, Monty Hall.
Thank you, and welcome.
Hi again, guys. It's Andrew, Dr. Droll again, here with my second demonstration. This one's a little bit sillier. So, if the video is working right, you just saw the introduction to Let's Make a Deal, an American TV show from the 1970s. And this is the game. So in this game, you have 3 doors, and you get to pick one. The game show host then reveals one of the other doors, and shows you a prize that you don't want to win, in this case a goat. And then he gives you the choice. Stick to your original door, the one you picked at first, or switch to the other remaining door, the one that he didn't open. So you can see I'm playing right now. I had picked door 2 originally, he opened door 3 and showed me a goat, and then he said that I could switch. And then I stuck to my original door, and I got a goat. So I lost. I didn't win the new car behind the first door. So there's one door with a really good prize, and there are 2 doors with prizes that you don't want. That's the game. So you pick a door, the host reveals one of the other 2 doors, which just has a bad prize. It does not have the prize you want. And then, trying to win the prize that you do want, in this case a new car, you have the choice of either switching or staying. And as you see, I just played again. This time I switched from door 2 to door 1, and I still lost. I just got the goat again. I didn't get the new car. And I can just keep playing to figure this out if I want. Now, why am I bringing up this problem? The reason I bring up this problem is because this problem reveals a deeper thing. In mathematics, it's an unintuitive result. So the answer is that there is a right choice. You should always either switch or stay. I'm not going to tell you the answer. I want you guys to play, or at least listen to the video a little bit more to figure that out. But one of the options, switching or staying, will give you a much better chance of winning. So you guys are going to be able to play this game on your tablets there during the Pi Day activities, and you can see what works for you. Now, why is this such a controversy? Well, part of it is because of this woman who I'm showing on screen right now. This is Marilyn Vos Savant. Marilyn Vos Savant was at one point indicated to be the most intelligent person in the world by IQ tests, tests of intelligence. Now these are fairly silly tests that are widely disputed, but she had a reputation and she wrote a column in a magazine, and at one point a reader wrote in and asked her about this problem. Should you switch or should you stay? And she told them confidently that you should switch. And she was right. You can actually show that it's a better strategy to switch. In fact, it's twice as good to switch as to stay. But many mathematicians were confused by this. They didn't agree with her. They thought that she was wrong. And so it became a large argument where establishing the right answer was very complicated, at least in the social sphere. The mathematics is actually fairly straightforward once you get your head around it. But for now, I suggest you guys just play the game. In fact, first, I'm going to play the game for you. I'm going to speed up the video and play the game about 50 times and show you how I do to see what's going on here. That way, maybe you'll get a better sense of things. And at the end, I'm actually going to show you the result of a simulation of this thing 1,000,000 times to see what happens. So, guys, as you can see, I played a bunch of games. And so after all that, I ended up playing 66 games where I switched doors, and 66 games where I stayed at the same door. I did not switch. I stuck to my original one. And how did I actually do with that? Well, let's see. So, you'll notice when I switched, I won a lot of cars. I won 46 cars when I switched doors. So out of 66 tries, that's better than 2/3. I won a lot of cars. 46 out of 66 means I won most of the time. I lost less than I won. So it's pretty good. In fact, I won about 70% of the time. That seems pretty good. And that's when I switched doors. What happened when I didn't switch doors? When I didn't switch doors, well, I also played 66 games. But I only won 22 cars. I mean, that's still a lot of cars. 22 sports cars, that's pretty good. But out of 66 games, that means I lost more than I won. I only won 1/3 of the time now. About 33% instead of 70% the other way. The other way, I did more than twice as well. So what's going on here? Is switching actually the better option? Well, the answer is yes. Switching is the better option, but I want you guys to play and see if you find the same experience. Let's see if we can figure out why switching is the better option, though. So, when we start the game, we have 3 doors, and we have to pick one of them, just one. So, let's say I pick door number 2, Or actually, let's say I pick door number 1, it's a little bit easier. So if I pick door number 1, it's kind of like I'm protecting that door. Because in the next phase of the game, the host has to open a door that's not the one that I picked originally. That's the rule. He won't open my door. He'll open one of the other 2. And he'll open one that has a goat behind it. And there has to be one with a goat behind it, because there were 2 goats to start with and only 1 car, right? So one of the 2 other doors must have a goat behind it. Now, at first, what was my chance of winning? Well, there are 3 doors. I'm picking one, basically at random. I don't have any information about it, right? So my chance of winning should be pretty bad. It's only about 1/3, right? So my chance of being wrong, in other words, was the rest of that. It was 2/3. The car is probably behind one of the other 2 doors. He's not behind my door, probably. Sometimes he will be. But okay, so I pick my first door, and the host opens a goat. Now I have 2 doors left, and it seems like these 2 doors are the same, right? Like there should be no difference. Like it should be 50-50, a flip of a coin. But actually, I protected my first door. So that means if the goat wasn't behind my first door to start with, then it's got to be behind the one that he's asking me to switch to. And that's a bigger chance, because if the car was in the other 2 doors, then it's behind the one that's left. And so when I pick that one, I have a better chance of getting the car, as we just saw when I won again by switching. Remember, I picked door 1 to start with. He opened door 3, showing me a goat. I switched to door 2, and I got the car. So actually, you have a 2/3 chance if you switch, and a 1/3 chance if you stay. So now, to finish off, I'm going to show you a simulation of 1,000,000 of these, and then you guys can play to try it out. So here, guys, I've got the code that'll let me run 1,000,000 copies of this game. This little snippet of Java code, it's in the Java programming language, will simulate the player and the host and the result. So what it's going to do is randomly guess a door. Then the host, which is really part of the program, will reveal one of the other 2 doors that contains a goat. And then the program will always choose to switch, and it'll tell me whether it won or lost. So if it lost, that means that staying with its original door would have won. If it wins, it means that switching doors was the right option. So we'll see how often switching is the right option versus staying. So here we're running the simulation. Each line here is one game that's being simulated. And in a minute I'm going to pause this. So as you can see, I'm highlighting a line, and this gives me all the information that I need about that one game. It tells me what number I guessed. Here the doors are numbered 0, 1, and 2 instead of 1, 2, and 3. It tells me my guess was wrong. It tells me the reveal was door 2, the last one, like door 3 in our regular game, and that I won when I switched because my original guess was wrong. So each line gives me all the information I need about one of the games. Actually, telling me the result of the guess is a little bit of cheating, because in the real game I don't know that, But the program doesn't cheat. The program's just telling me that information. It's not using that information to run the game. So, and I know that because I wrote the code for the program. I know exactly how it works. So this game is randomly simulating everything. It's randomly simulating the guess. It's randomly simulating the reveal, which must be a door with a goat behind it. And it's telling you which way it won, whether switching one or whether staying one. And we can see in a minute, as we get up towards the end here, right at we're at guess number 850,000, which option won more often, whether switching or staying is the better option. And so in a second we're going to be finished. We're getting close to 1 million here, guys. Let's see what the result is. Alright, we're done. Oh my gosh. So let's see. We've run 1 million trials is what this is telling us. Switching won 666,870 of those million times, whereas staying won 333,130 times. Those are the same as when switching lost. So we won 66.687% of the time. Now, 2/3, which is what I told you the chances were of winning if you switch, is 66.667%. We're so close, but that's just what we expect if the math is right. So this tells us we're probably right with this. And now, guys, you go and play, and you tell me what result you got. Have some fun. See you. Thank you.